Imagine holding a fragment of Roman concrete under high magnification imaging. Your eyes would find countless gray crystals, volcanic ash bound in calcium. But scattered throughout, you'd notice something peculiar. Bright white chunks, some as large as pebbles, riddled with microscopic fractures. For nearly 2 centuries, scholars assumed these were mistakes, lime that hadn't mixed properly, evidence of rushed construction or incompetent laborers. But in 2023, researchers at the Massachusetts Institute of Technology discovered something remarkable. These supposed flaws were the secret ingredient, the mechanism that let Roman concrete heal its own wounds. Quick note, this content is educational only, based on peer-reviewed archaeological and materials science research. Now, run your fingers across the surface of ancient concrete. The texture is rough, granular. If you could crush one of those white fragments, you'd feel chalk between your fingers, calcium oxide, quicklime, and if you added water to it, you'd smell something sharp. Mineral, alkaline, the substance would grow hot in your palm. This is the chemistry the Romans harnessed 2,000 years ago. Consider this. The Romans left us detailed architectural manuals, complete with mixing ratios and material sources. Yet modern engineers couldn't replicate their durability. What were the texts not telling us? The Roman building boom began in earnest during the late Republic. The Pantheon, aqueducts stretching hundreds of miles, massive harbor complex at Portus, all structures requiring unprecedented durability. They needed concrete that could withstand ocean waves, support colossal domes, channel water across mountain ranges for centuries. The architect Vitruvius documented recipes in his treatise on architecture. He wrote that if you add ground pottery shards to river or sea sand in the proportion of 1/3 part, the mortar will be better for use. The text is precise, methodical. It shows Romans documented their processes meticulously. But Vitruvius omitted something crucial. He never described the thermal preparation of lime. Pliny the Elder, writing in the 1st century, complained about building collapses in Rome. He blamed them on what he called the purloining of lime, the theft of quality materials, the laying of rough stones on each other without proper binding. Pliny understood that lime quality was critical, but he didn't articulate the mechanism. He couldn't. The chemistry was invisible to him. The volcanic ash component was well understood. Pozzolana, named after the town of Pozzuoli near Naples. Romans quarried it by the ton, mixed it with lime and aggregate, built an empire on it. Yet here's the mystery. Some Roman structures lasted millennia. Others crumbled within decades. Same ingredients, same general recipe. Vastly different outcomes. What was the variable? For centuries, no one knew. Then, in 2023, a team led by Professor Admir Mazik at MIT examined ancient concrete samples with high-resolution microscopy. What they found changed everything. Let us examine the chemistry. Traditional assumption held that Romans used slaked lime, calcium hydroxide. This is lime that has been soaked in water before mixing. It's safer to handle, produces a more uniform paste. This is how modern lime mortar is made. This is what scholars assumed Romans did. But chemical signatures in the ancient samples told a different story. The evidence suggests hot mixing, adding quicklime, calcium oxide, directly to dry volcanic ash, then adding water. What happens next is dramatic. The quicklime reacts with water in an exothermic reaction. Temperatures spike. Some batches would have reached 200 degrees Celsius. Hot enough to burn exposed skin. Hot enough to create steam. Hot enough to fundamentally alter the crystalline structure of the calcium compounds forming in the mix. This violent reaction produces something unexpected: high surface area lime. Clasts, brittle calcium-rich fragments embedded throughout the concrete matrix. For nearly 200 years, archaeologists saw these fragments and assumed they indicated poor quality control. They were wrong. What's remarkable is that the very brittleness of these lime clasts, what researchers mistook for weakness, is what allows them to fracture before the surrounding matrix does. Cracks in the concrete preferentially travel through these brittle lime clasts. It's the path of least resistance. Here's what happens when a crack forms. Water enters the fracture. The crack has exposed fresh calcium hydroxide from the broken lime clast. The water reacts with this calcium hydroxide, produces a calcium-saturated solution. Then, over days or weeks, that solution recrystallizes as calcium carbonate, filling the crack, sealing it. The concrete heals itself. Professor Masik's team didn't just theorize this. They tested it. They created modern concrete using the hot mixing technique. They deliberately cracked the samples, half-millimeter fractures. Then they exposed the cracked concrete to water. Within 2 weeks, the cracks had healed completely. Water could no longer penetrate. The mechanical strength had been restored. We might imagine the scene at a Roman construction site now. Not the orderly process we picture from Renaissance paintings, but something more chaotic, more dangerous. Laborers hauling baskets of quicklime from kilns. The lime still warm from roasting limestone at over 900 degrees. Workers mixing it with volcanic tephra on site. The sound of rough stone grinding against reactive powder. Then, water is added. Steam erupts from the mixture. The batch grows hot to the touch. This is not a mistake. This is the Hien process. This heat is creating those microscopic reservoirs of reactive calcium. Reservoirs that will wait dormant until cracks form decades or centuries later. In 2024, excavations at Pompeii revealed something extraordinary: an actual Roman mixing site, preserved in volcanic ash from the eruption of Vesuvius in 79 AD. Archaeologists found quicklime particles in the atrium mixing area. Not slaked lime, quicklime, direct physical evidence that hot mixing happened on site, just as the chemical analysis suggested. Now, let's address a common misconception. The popular image shows Roman engineers guarding arcane formulas, secret recipes lost to time, a civilization that possessed knowledge we've somehow forgotten. But the evidence suggests something different. They weren't hiding secrets. They simply never wrote down what seemed obvious. That lime should be added hot, not pre-slaked. It was folk knowledge, the kind transmitted through apprenticeship rather than text. A master builder shows an apprentice once. The apprentice does it that way for 40 years, teaches his own apprentices the same method. No one thinks to record it. The volcanic ash component has been studied since the 1700s. Modern concrete already uses similar pozzolanic additives. Fly ash from coal combustion, silica fume, ground slag. We didn't lose that knowledge. What was missed for 2 centuries was the preparation method, not the ingredient list. The lime clasts were visible in every sample. Every fragment of ancient concrete examined since the 1800s contained them. But researchers dismissed them as contaminants, or as evidence of poor mixing. It took high-resolution microscopy and advanced chemical analysis to reveal their true structure, their true purpose. It seems that what we label as ancient wisdom is often ancient pragmatism. The Romans didn't understand the chemistry the way we do now. They didn't know about calcium carbonate precipitation or crystal nucleation, but they knew what worked. They observed, they iterated, they built. And now, 2,000 years later, we face a crisis they never imagined. Modern concrete production accounts for roughly 8% of global carbon dioxide emissions. It's one of the most carbon-intensive industries on Earth, and the structures we build begin cracking within decades, requiring costly repairs or complete demolition and replacement. Roman concrete in marine environments has gotten stronger over time. The harbor at Portus, submerged for 2 millennia, seawater continuously reacting with the pozzolanic minerals, creating new crystalline bonds, reinforcing the matrix. Our concrete dissolves in seawater. Theirs thrived in it. Professor Masik's team is now commercializing hot mixed concrete formulas, not as historical recreation, not as novelty, but as a solution to 21st century infrastructure decay. Early tests suggest these formulas could extend concrete lifespan by decades while reducing the need for steel reinforcement. What remains visible today is testament to their engineering. The Pantheon Dome in Rome, 142 feet of unsupported concrete, still the world's largest unreinforced concrete dome after 1,900 years. Rain falls through the oculus. Water streams down the interior surface during storms. For nearly 2 millennia, that water has been seeping into microscopic cracks, activating those embedded limeclasts, recrystallizing, healing. The dome endures not because it never cracks, but because it was built to repair itself. Here's what matters. The Romans didn't have our materials. Science. They couldn't model stress distributions with finite element analysis. They didn't understand chemistry at the molecular level. Yet they embedded self-repair into their most important structures. By observing what worked, preserving reactive components within the matrix, by building not for permanence, but for resilience. The next time you see the Pantheon's dome, 142 feet of unsupported concrete, lit by a single oculus, consider the possibility that embedded within it are millions of microscopic limeclasts, waiting for cracks that may never come, or for water that might activate them centuries from now. The Romans built expecting failure, but engineered for recovery. Perhaps that's the deeper lesson. Not permanence, but resilience. Not perfection in construction, but wisdom in anticipating decay. 2,000 years separate us from the workers who mixed that hot lime and volcanic ash. But the chemistry they harnessed still functions today, still heals, still endures. That fragment of concrete under the microscope, those bright white chunks we once dismissed as flaws, they're waiting too, ready to dissolve, ready to recrystallize, ready to bind stone to stone one more time.